So before we start today, I want to talk to you guys about homework, in as much as I have forgotten to post any in a bit. So there's obviously material that I would like to have covered in the homework from the the steady state sinusoidal power stuff. What I am considering doing is just putting up like 4 homeworks for the rest of the quarter, and then just making them all due on the last day of the quarter or something like that, so that I stop forgetting to post them. Would anybody be opposed to something like that? So that would include all of the homework that I missed previous, and then the homework that I intend to assign on this upcoming material, which we've got just shy of 2 weeks to cover. Anybody got any problem with that? Oh, okay. All right, so since nobody's saying anything, I'm going to assume that we're all good. I saw some head nods. Let's see what's going on here. Sounds good. Okay, so today we are going to start talking about 3-phase circuit analysis. Okay, this traditionally is one of the hardest sections of material for the students to understand, and I fundamentally do not get why. It is nothing more than what we did in the steady state sinusoidal analysis, except that now there's 3 of them. That's it, okay? There is some jargon that is associated with it that can be a little bit daunting. And so really what we're going to spend today on after the introduction is trying to wrap our heads around that jargon, so that when we get into the actual circuit analysis bit, I will know what I am talking about, and you will also know what I am talking about, and it will not just seem utterly foreign to you, okay? So with that in mind, let's begin. All right, so introduction to 3-phase circuits. All right, so up to this point, pretty much every circuit we have analyzed, at least in the steady state sinusoidal case, has been some variation of a single phase circuit. Now, you may not totally agree with this, but I would argue that it's actually fairly accurate if we consider the Thevenin equivalent. So let me explain what I mean by a single phase circuit, okay? So I might have, that looks like garbage. Circuit that looks like this. I'm going to call this VP angle theta V, where VP stands for a phase voltage. We'll talk about that in significantly more detail in a little bit. So in this circuit, why I'm considering it to be representative of everything that we've covered before is because we could boil down effectively all of the circuits into something that looks like this, just using Thevenin and Norton equivalent circuits. So in this circuit, I'm going to break it up into 3 discrete sections, okay? We have on the left, what I'm going to call our source section. And from here on out, I am going to make a point to use lowercase subscripts for quantities that are associated with the source side of things. On the right-hand side, we have our load section, and I'm going to make it a point from here on out to use uppercase subscripts for the load side of things. And then everything in the middle would be what we consider transmission lines. And while we're talking about things, for our single phase circuits, we typically have a hot wire and a neutral wire. There isn't necessarily a ground, okay? The neutral wire serves as our reference in a single phase system. And in a practical single phase system, it might be connected to earth ground at some other stage in the system, but it may not, that connection to earth ground isn't part of what's going on. So that's why there are 3 holes in the receptacles on the walls, okay? One is for the hot, one is for the neutral, and the little bitty one is the earth ground connection that ties to that. And that's just for protection purposes, which is why you can get adapters that don't have the earth ground connection and all that kind of stuff. It will still work dangerously if you were to snip off the earth ground pin on your plug or something like that. You might burn something down, but it'll still run until it reaches an overcurrent state that earth ground connection was supposed to prevent. So anyway, so this is what we are largely used to dealing with, okay? Now I'm going to draw what's called a 3-phase, 3-wire system. Okay. So in a 3-phase, 3-wire system, we are going to have 3 voltage sources. Like so. I'm going to call this guy VP with an angle theta A. This guy down here, VP with an angle theta B. And VP with an angle of theta C down here. We're still going to have some transmission line, but now we're going to have 3 of them. These are going to be connected to a 3-phase load. So I'm going to call this ZLA, representing the A phase of the load. ZLB for the B phase of the load. And ZLC for the C phase of the load. And we can subdivide this circuit into 3 parts as well. So we have our source, our transmission lines, and our load. Never mind, I was going to talk about something about why these transmission lines aren't really transmission lines, but I don't think you guys have had enough physics yet to understand what the difference is. So it's literally just confusing. So for now, let's just call them transmission lines and leave it at that. Instead of having a hot wire and a neutral wire, this system actually has 3 hot wires. So we would call one the A phase line. This guy down here would be the B phase line. And this guy down here would be the C phase line, okay? This system does not have a neutral. If we wanted to have a neutral, I'll do it in gray just for the sake of argument. The neutral connection would be something like this. So We would call this guy lowercase n because it's on the source side, this guy capital N, and here is our neutral line. This makes it a 4-conductor system, okay? So some of you may be asking, why do we use 3-phase systems? Anybody have any idea? I guess it depends on what you mean by split the load. Okay, so let's say we're looking at this first system here, right? We could deliver a certain amount of power to our load using 2 wires, our hot line and our neutral wire, okay? And our second system, with the neutral wire neglected or taken off because we don't strictly have to have one, we can deliver 3 times as much power using only 1.5 times as much wire. So it's literally cheaper. If we have a system that includes the neutral line, we're still delivering 3 times as much power with only twice as much wire. Right? Yeah. So we are still at a cost advantage there. So that's the main reason that 3-phase power is used really everywhere that we want long-range transmission of electric power. There is another advantage that has to do with electrical machinery. And when we get into the power analysis, it will become evident. But a 3-phase voltage system like our source here is capable of creating a constant torque in a rotating electric machine. So what that means is that if the torque is constant, effectively the motor doesn't vibrate. And if the motor doesn't vibrate, it's not damaging itself during operation. So we get much more efficient operation of rotating electrical machines like induction motors and stuff like that if we're using 3-phase power. If you're only using single-phase power, there tends to be a little bit of wiggle, and that little bit of wiggle wears out bearings and stuff like that and causes higher maintenance costs. So the main reason we do it is because it's cheaper. A secondary reason is because it makes electric machinery, which is the foundation for manufacturing across the globe, less costly as well. All right, so let's take a look here on the source side of things specifically and talk about 3-phase voltage generation. So at a power station, an electrical generator is used to convert mechanical energy into electrical energy via induction. So what we have in that system, and this is going to be a crappy drawing, so I apologize, but it is the best I can do. We have a magnet. It has a north pole and it has a south pole, and it is allowed to rotate along its central axis. Let me do that in orange. And so I'm just going to arbitrarily say that it's rotating counterclockwise with an angular frequency of omega. Okay. This part here in the middle is what's called the rotor. Outside of the rotor, we have what's called the stator. Sorry. Trying to draw a not terrible circle. Not going to go well. So here is our stator. And a stator is just a stationary magnet. Okay. And there are coils associated with the stator, okay? So I'm going to call this guy here A, and then this guy down here will be A prime. I'm going to call this guy B, and this one directly opposite it is then B prime, and then this guy over here would be C, and this guy directly opposite that would be C prime. And sorry, I'm going to do A as blue, B as black. I might be getting these backwards, but it'll be okay because you guys aren't going to go lick an electrical panel. And C as red. And I'm going to do all the others, I'm going to fill them in gray. Okay. We attach wires to these coils. So for instance, right out here, this would be my A terminal. All of my prime things are going to be attached together. Like so. And these are tied to my neutral conductor. Here is my C. So I'm going to jump that guy. And here is my B. Like so. Okay. So this is a crappy drawing, but I'm trying to just explain what's going on. I guess it might help. Let me just try to fill this region in to let you know that this is, that's all the state. Okay. So what's going to happen is as this magnet rotates, at certain points in its rotation, the magnetic flux seen by A, B, and C will be at its maximum, which will cause the voltage drop that occurs between terminals A in the neutral, B in the neutral, and C in the neutral to be at its maximum as well. Okay? So what it's going to look like, let me draw these voltages here. So between B and N, we're going to have a voltage VBN that's an RMS phasor. Between C and N, we're going to have a voltage VCN that's an RMS phasor. And between A and N, there's also going to be a voltage, but it's hard for me to draw it on this thing, so I'm not going to worry about it. Okay? But there is some voltage VAN as well. So let's say that we plotted these guys in time. So at the point that I have drawn on the circuit, the north pole of the magnet is directly lined up with the A phase of this guy, and the south pole of the magnet is directly lined up with the A prime coil. And so that means that would be the start of our cosine signal. Okay, so that means it would look something like this. All right. Well, because the B coil is physically located 120 degrees away from the A coil, we'll see that B should reach its peak at a shift in phase of 120 degrees later, okay? So that means it'll look something, let's see. So that's 1, 2, 3. So something like this. And then finally, our C phase is 240 degrees removed from our A coil. And so it will be shifted by 240 degrees there. Yes, sir. So I would say that in this system, with omega drawn in this particular direction, B is lagging A by 120, and C is lagging B by another 120. Because based on where we've started, it hits A first, and then B at a later point in time, and then C at a later point in time. But if it were rotating the opposite direction, you could say that C is lagging by 120, and B is lagging by 240. So it all depends on the rotational direction, which is called the phase sequence, which is the next thing I'm going to talk about after I finish drawing this picture. It's okay. You would choose the phase sequence that gets you the rotation in the direction you want. So if you want your motor to spin counterclockwise, you hook it up one way, and if you want it to spin clockwise, you hook it up the other. So in Engineering 120, when you guys were playing with the little DC electric motors for your pumps, did you happen to notice that if you connected your voltage polarity in one way, the motor spun in one direction, and if you did it the opposite way, it spun in the other? The exact same thing holds true even for three-phase motors. So if you effectively switch the B and C connections, it spins the opposite direction. So that's really the only difference between those two. So you hook it up one way to make it spin clockwise, the other way to make it spin counterclockwise. One way has what's called a positive phase sequence, the other way has what's called a negative phase sequence. From a circuit analysis perspective, it's the exact same thing, except that all your angles will have plus signs instead of minus signs. So, all right, so for my C phase, it's going to look something like this. And I'm going to say that VAN, as a function of time, will be VPA cosine omega t. VPB of t, I'm getting ahead of myself, VBN, apologize, VBN of t will be VPB cosine omega t minus 120 degrees. And VCN of t will be VPC cosine omega t minus 240 degrees, which would be the exact same thing as positive 120 degrees. So I choose, this is pretty much the only case where I typically have an angle that is a magnitude of greater than 180 degrees is when I'm dealing with a three-phase system. It does not hurt my feelings if you all use 0, plus 120, and minus 120 as your references and all that kind of stuff. Doesn't bother me one bit. It's just not the way that I particularly choose to do it. Okay. So just to be very, very clear here, The reason why these three voltage signals are 120 degrees out of phase with each other is because the coils are literally physically separated by 120 degrees around the circumference of the stator, okay? If they were not 120 degrees separated, then we would not have this 120 degrees phase separation, which is critically important to having this thing work out very, very well with that no vibrations occur, okay? Now, another thing that I want to point out right now, I have listed that the A phase has a magnitude of VPA, the B phase has a magnitude of VPB, and the C phase has a magnitude of VPC. It would be extraordinarily unusual for these guys to not have the same magnitude, okay? They all have the same magnitude because they're built by robots to have the exact same number of turns in the coil, okay? So that means they're all going to experience the exact same amount of flux and experience Faraday's law of electromagnetic induction in the exact same way to generate the exact same voltage magnitude, but they're just going to be out of phase by exactly 120 degrees, okay? So for the only way that that wouldn't happen is if there was some sort of mechanical damage that caused a short where one coil looked smaller than the others. That's the only way that you would get the voltage not to be the same. The reason why I'm making a point to kind of harp on this is because we're going to be talking about balanced three-phase circuits. And one of the biggest assumptions that we're making is that our source is a balanced three-phase source. For it to be balanced, the magnitude of all of the voltages has to be the same, and they all have to be separated by exactly 120 degrees. That does not, like that happens 99.999% of the time. The only way to get an unbalanced source is to physically screw it up. So that's never going to be the issue effectively. It's always going to be something on the load side that's going to set up all your imbalances. Okay, so I just wanted to be clear about that.
So the margin of error for the robots is
very, very. So we're talking about you might be off by tens of millivolts when you're outputting 400 volts RMS. So it's very, very small. Okay. If you've ever watched How It's Made, or particularly How It's Made Dream Cars, the episode when they're building the Tesla Model S actually goes into a lot of detail on how they're building a three-phase motor because the Tesla Model S's use three-phase motors for their drive system, all based off of use a battery that goes into an inverter to create the sinusoidal signals, and then it uses three-phase because it's the most efficient way to deliver power to each of the four-wheel assemblies at the same time. Anyhow. So with these signals, we can represent them in the phasor, or excuse me, the RMS phasor domain pretty easily, right? So I could say that this guy is going to be some RMS phasor voltage VAN with a phase angle of 0 degrees. This guy is going to be some RMS phasor voltage VBN with an angle of negative 120 degrees. And this guy leads me with an RMS phasor voltage of VCN with an angle of negative 240 degrees, where we get the magnitude of these guys just by dividing their magnitude by square root of 2, right? Okay, so now we talk about phase sequence, all right? We have two different possibilities for phase sequence. So positive, also known as ABC sequence, occurs when omega is counterclockwise, and we will see that VAN is equal to VP with an angle of 0 degrees, VBN is equal to VP with an angle of negative 120 degrees, and VCN is equal to VP with an angle of negative 240 degrees. A negative phase sequence, or CBA sequence, omega is just clockwise. And so we find that VAN is still our reference, so it's going to have VP angle 0. VBN is now going to lead by 120. And VCN leads VBN, so we have VP angle plus 240 degrees. In this class, I'm going to do everything with a positive phase sequence, just so there's no ambiguity or anything like that. I will either call it positive phase sequence or ABC phase sequence in the problems. If for whatever reason I forget, just assume that it is a positive phase sequence. So that means that B lags A by 120 and C lags B by another 120 degrees. Okay? What's up? CCW, counterclockwise. Or if you're British, anti, makes you feel better. All right. Does anybody have any questions on this voltage generation stuff? Now, I mean, this isn't a physics class, so we're not going to go into the great details of electromagnetic induction and all that kind of stuff, but do you generally accept that there is a magnet that spins around, which causes voltages to occur? If you go to the door, if you go that way, and then take a left down that hallway before the exit door, there is a rack that has 3 electric machine rotors on it, actually, so that you can go look at them if you ever particularly felt like it or whatever. But it's just a long shaft with electromagnetic coils on it. That's all it is. So we don't actually use a permanent magnet or anything like that in 3-phase motors because it would be actually too expensive. We use electromagnet to do it, but it's all the same. All right, so with that out of the way then, let's talk about source and load configurations. And this is where the jargon starts to bite us in the butt, okay? So we will start by talking about a Y-connected source. So you might see it some places as WYE. Other places you will literally just see it as the capital letter Y, okay? There are a couple of different ways to draw it. I will show you the 2 that are most common. Like so. Okay. This is probably the most common way to draw this particular configuration because you can easily see why it's called a Y-connected source, okay? It is 3 voltage sources. They are all 120 degrees out of phase with each other. They share a common neutral point, which is that neutral conductor there in the center. But it is A, a pain in the butt to draw, and B, I feel confusing. So I prefer an alternative drawing like the one I did before. So my personal preference, you do not in any way, shape, or form have to follow this. We have the A phase, B phase, and the C phase. So this would be voltage VAN, VBN, and VCN. All right. So before we move along here, I want to explain the double subscript notation that I'm using because some of you may not be familiar with it, okay? So as I said previously, I'm using lowercase letters to denote that we are on the source side of our system. The first letter in the subscript, in this case A, denotes the positive polarity terminal of the A phase voltage source, and the N is where the negative polarity terminal is connected. So that's why we have VAN, VBN, and VCN, okay? These quantities are what are called phase voltages. All right, so a phase voltage is a voltage drop that occurs over one phase of a source or a load. Okay. So we would say that our source has a phase voltage of VAN, a phase voltage of VBN, and a phase voltage of VCN. We can also measure what are called line voltages. Okay. And a line voltage is simply the voltage drop measured between the transmission line terminals. Of a source or load. So I'll do these in a different color. Okay. So for instance, we would have a line voltage of VAB here between the transmission line terminals A and B for this set. On this guy, it's going to look like this. We would also have a voltage VBC. And we could also have a voltage VCA. So our line voltages are VAB, VBC, and VCA. All right. We can next define what are called phase currents. Where phase currents are the currents flowing through one phase of a source or load, I choose to define them as always flowing into the positive polarity terminal, okay? Even for sources, I just choose them arbitrarily to be flowing into the positive polarity terminal, so that when I'm dealing with a source, the product of the voltage and current is the supply power. When I'm dealing with a load, the product of the voltage and current is the absorbed power, okay? So that would be IAN, IBN, and ICN, okay? So the first subscript letter is where the current is originating from. The second subscript letter is where the current's going. And I could do it similarly on this side. IAN, IBN, and ICN. Okay. Now, there are such a thing as line currents, okay? But we can't look at them when we only have a source. Line currents are fundamentally just the currents flowing through the transmission lines. If we are looking only at a source without the rest of the system, the line currents do not exist. So we will address those once we start getting into the circuit analysis portion. So for now, the only quantities that we're concerning with ourselves with are phase voltages, line voltages, and phase currents. So before I move on to the delta connected source, does anybody have any question about where any of these things come from or why I chose to call them a particular thing or anything like that? Yes, sir. So our phase currents is the current that's flowing through each phase of our voltage source, okay? So there's going to be one that flows through the B phase, one that flows through the A phase, one that flows through the C phase. They are named in such a way that they flow from C into the positive polarity terminal, out the negative polarity terminal to the neutral. So it's always where they're originating from as the first letter, where they're going as the second letter. Did that answer your question? Okay. Any other questions on these? And to be clear, the voltages, positive polarity terminal is the first letter, negative polarity terminal is the second letter. So that's how we're going to do all these things. It's going to be way easier to do a double subscript notation than anything else here. All right. Now let's take a look at a delta connected source. So you may see it as written out as delta, or as the Greek letter delta, or a triangle. And so what this guy is going to look like something like this. So this is VAB, VBA, and VCA. Okay. There is no neutral connection for a delta connected source. Okay, so there is no place to put a neutral wire, even if we wanted to. All right, they're just all strung up kind of in series in a circle like that. All right. Another way to represent this, and this is another case where it's my preferred method, but again, you do not have to do it. Is like this. Here is C, B, A. Here is voltage VCA, VAB, VBC. All right, so what are my phase voltages in this system? I've already written them down, right? They're the voltage drop over one phase of the source. So that would be VAB, VBC, and VCA. Anybody have any ideas what my line voltages might be? The exact same thing. Okay, so here would be VAB, here would be VBC, and we could do VCA like this. So this is one of the spots where things get a little confusing, right? For a delta connected source, the line voltages and the phase voltages represent the exact same quantities. But for a Y connected source, that isn't true. Okay, so that's why it's fundamental for us to know what a line voltage really means and what a phase voltage really means. Because in a delta connected source, I can ask you for one and you can give me both. But in a delta connected, or excuse me, in a Y connected source, if I ask you for one, you can't just tell me what the source voltage is because it's going to be something entirely different. There's mathematical relationships that we're going to develop and all that kind of good stuff. But this is where the jargon starts to bite you in the butt. Okay. What are our phase currents going to be? Right, so this one right here would be IAB. This one right here would be IBC. This one right here would be ICA. Like so. Okay. Any questions on the delta connected source? All right. So these are our two different source options for a three-phase system. So now we need to talk about the two different load options, which are the delta connected load and the Y connected load. All right, so let's talk about the Y connected load first. So that's going to look something like this. All right. This is our neutral conductor here in the middle. So because I'm on the load side of things, I'm looking at everything in terms of capital letters. The alternative way to draw this be like so. This is A, B, C, and this point is N. So what are my phase voltages going to be? Incorrect. Those would be line voltages because they're measured between the transmission line terminals, right? My phase voltages are going to be the voltage drop over one phase. So I would have plus minus VAN. That would be one. All right. Plus minus VBN would be another. Plus minus VCN would be my third. Okay. So it's the exact same thing as we saw for the Y connected source. We just use capital letters because we're on the load side. VAN, VBN, VCN. Our line voltages, Mr. Bailey, I believe already got us started on those. So those are the ones measured between the transmission line terminals. So VAB, VBC, VCA. And finally, our phase currents are going to be what? So same thing as the phase voltages, but I instead of V, right? That's always going to be true. Phase currents and phase voltages are going to be the exact same subscripts. Just one's going to be V for voltages, obviously, and the other one's going to be I for currents. So that would be IAN, IBN, and ICN. Oh, I did them in the wrong colors this time. I apologize. I'm backwards. All right. Any questions on Y connected loads? So what do you think is going to happen with the delta connected loads? It's going to be almost exactly the same as the delta connected source, except everything is going to have capital letters. All right. So that's going to look something like this. Oh, sorry, it's a load, so it should be a box. Where we'll call this guy Z delta A, this guy Z delta B, this guy over here Z delta C. A, Z delta B, Z delta C. All right, so because it's a delta connected something, it should be fairly easy to see that our phase voltages and our line voltages are going to be the exact same quantities. So in this case, that'll be VAB, VBC, and VCA. And then our phase currents. IAB, IBC, and ICA. All right, so everybody feel comfortable with the different source and load combinations, phase voltages, line voltages, and phase currents. Okay, so we got 13 minutes left in class. That's not enough time for me to get into the circuit analysis, but I will draw a system, and I'm going to ask you guys to identify some stuff, okay? And this is actually going to bring us up to the concept of line currents as well. So All right, who am I going to pick on? Mr. Warland, you look like you've been paying attention probably. What is my phase current through, actually, here's a better question. Let's start with something easier. What kind of system is this? Now, typically speaking, we denote a system by the type of its connection on the source side and then the type of its connection on the load side. So is this a YY system, a Y delta system, a delta Y system, or a delta delta? Remember, the first letter is, or the first notation is for source, second notation is for load. So this is a Y delta system. Does everybody agree with that? Okay. Race. What is the phase voltage in the C phase of the load? Yeah. Oh, no, sorry, you're Jace, not Race, right? I apologize. And the C phase of the load. What is the, did I say phase voltage? Yeah, phase voltage for the C phase of the load. Tell me what it's supposed to be. I don't have any of them labeled, so you got to know what you're doing. So where is the neutral connection for the load? There isn't one, so it can't have an N in it. Yeah. All right. VCA. It'll always be CA. AC. So, I mean, it really doesn't particularly matter, but because we're dealing with a positive phase sequence where we want the C phase to be 240 degrees lagging the A phase, we'll go CA. So the phase voltage across the C phase would be this guy right here, VCA, okay? Young lady whose name I don't know. I apologize, let's start there. What would be the line voltages between the A and B phases of the source? Okay, so it'll be VAB, lowercase letters though, right? So this guy right here, VAB. So that is the line voltages for the A, between the A and B phases. All right, so just while we're at it, our phase voltages are just going to be VAN, VBN, and VCN, right? And our other phase, our other line voltages would be here, VBC, and then from here to here, which would be VCA. All right. For the delta connected side, all of our phase voltages and line voltages are going to be the exact same quantities. Let me ask a more difficult question. Okay, so I'm going to introduce the concept of a line current now because we have a full system that we can look at. All right. For all the other questions I could possibly ask you, you could literally look back. If I wanted a source quantity, you know that it's a Y-connected source. We made a list of all of the different things. For the delta load, we literally made a list of all of the different things. So you know what I could possibly be looking for, okay? So a line current is current flowing through transmission line. That's simple, or flowing through the transmission lines, I guess would be another way to put it. So let me do this in blue. So our line currents would be I lowercase a capital A, because they originate at the transmission line terminal on the source side and terminate at the transmission line terminal on the load side. We would also have I lowercase b capital B and I lowercase c capital C. So, one of you gentlemen way in the back, tell me what my phase currents are going to be in my source. Okay, so IAN, BN, CN, etc. So they'd be directed in this direction. What is the relationship between my phase currents in the source and my line currents? They're the exact same thing, they're just opposite of each other. What if I had a Y connected load? What would be the relationship between the line currents and the phase currents in a Y connected load? So if I had a Y connected load, for the sake of argument, let's scribble one in here real quick. Yeah. So my currents, my phase currents would be in this direction. They would be identical to my line currents, okay? So that's something that we need to kind of keep in our head as a little bit of a shorthand to help us out, okay? In a delta connected anything, the phase voltages and the line voltages represent the same quantity. In a Y connected something, the source currents, or excuse me, the phase currents and the line currents are closely related. I can't say they're the same thing because of the way that I've defined the phase currents for sources. They're in the opposite directions, but they'll at the very least have the exact same magnitudes 100% of the time. All right, I think that's enough out of me for today. So there's not going to be a homework assignment per se on what we did today. We didn't do any math whatsoever. What's up?
So we had one row, all three sources in parallel. We had one with four more series. There, all three.
Repeat what you just said because I don't think I agree with any of it.
BA, BB, and BC. Is there any agreement for all three sources?
No, but I mean, I would say the delta connection is the one where they look like they're in series, but they're never in parallel either. They're never all in series and they're never all in parallel. For them to be in parallel, they would have to share both sets of terminals, and that literally never happens, because if it did, if all three voltages were in parallel, they better all have the exact same voltage, or else you have a short circuit somewhere that's going to start a fire, right? And so what I mean by that is, if I have a system, this is just a quick aside. Let's look at a DC circuit. I have 5 volts in parallel with 4 volts in parallel with a 10 ohm resistor. What's the voltage drop over my resistor? The correct answer is beats the hell out of me, okay? If you have 2 different voltages in parallel with each other, circuit theory breaks down. Now, the reason why it's breaking down is because we are saying that this short circuit doesn't have any resistance to it whatsoever. In reality, if we had a wire connecting 2 different voltages that had connecting 2 different voltage sources in parallel that had 2 different voltages, what we would see is that current is going to flow through the wire. And it's going to be a whole heck of a lot of current because it's a very small resistance. So this is why way back in Engineering 120, Dr. Corbett or whoever your teacher was harped on you to constantly make sure the batteries were taken out of your battery box until you had it soldered to the barrel jack. Because if you didn't do it, you would be putting that 9 volts in parallel with 0 volts or a short circuit, and you would just drain your batteries and melt everything. This is that, but a little bit more formally. If they were both 5 volts, that would be perfectly fine. That is exactly what is done when you're doing solar panel installations and all that kind of stuff. You might actually have some connected in parallel and some connected in series. So like the reason why you would connect voltage sources in parallel is to get more current out of the system. So if you had 2 batteries and they were each rated for only 1 amp, if you connected them in parallel, you'd be able to supply 2 amps out. Whereas if you had 2 batteries rated at 5 volts and 1 amp connected in series, you'd be able to output 10 volts, but you could only get 1 amp of current, if that makes sense. So if AC, the AC problem is going to be a similar thing. So it's just going to be a sinusoidally varying large short circuit current flowing through your system if you tried to wire them up in parallel. So for AC systems, you have to be even more careful because you could have the same magnitude, but different phases will still screw things up, right? My job in Bossier, where I'm designing battery energy storage systems, is literally connecting huge batteries like 1500 volt batteries in parallel to be able to supply megawatts of power to something downstream. But it's all preconditioned on the fact that all of the voltages are going to be approximately the same, because if they aren't, things are going to break real fast. So much so that we have battery control systems that it will literally switch on and off different parts to maintain charge levels across the battery system. Anyway. All right. So that's enough out of me. I will see you guys on Wednesday. I'm going to put homework and stuff up. Yes, sir.
Can you show the again?
I don't have enough energy density to be a bomb per se, but it could definitely start a fire.
You can do that with a gum wrapper.
Yeah, with the cinnamon gum wrappers that have the foil on it. Yeah, that's a good way to literally start a fire if you're at a campsite. You take the battery out of your flashlight, use that gum wrapper, short it, it'll create a spark. Use that to set your kindling off. That's it's an old Boy Scout trick, I think.
I was so engrossed in what you were saying. I just don't want.
I'm a captivating fella. I don't know what else to say.